No. Hello, everyone. Today is the first key tech that we are doing, coming from the 100% tech community of around some artificial intelligence. So we've been working around this subject with a community of 8 people, and Stefan and I included. So Stefan and I, we're going to do the first key tech today, and it will be in full English. It's a first for key consulting, but it allows our friends in other countries to understand. And also, this will be available on YouTube and possibly with transcript in French for those who don't understand everything, or our weird accents, or maybe some stuff we say and you don't understand, so you can have the translation. Um, do you want to say something, Stefan, or should I start?
I know you can go on.
Okay, so basically this presentation is going to be about demystifying what LLMs are, so large language models, and a bit about artificial intelligence, and not go too deep into details, but just like touch the tip of the iceberg and what's the hype about this, and exactly what are those LLMs that everybody is talking about. And this will be the first, because other key techs are going to come on AI about stuff that are bit based on LLMs and other. So, okay, if I have control, what we'll see. So this is the summary. The history of AI and LLMs, particularly, I'm not going to do the whole history of computer science. What are LLMs? How does it work? How do they work? How are they made? What is fine-tuning? What LLMs do great? The current limitations of LLM, and what's the future, and some conclusion about AI and LLMs. So about the history of AI and LLMs. So basically, not going to do a big into details, but so starting in 1943, Ryan McCulloch and Walter Pitts published a paper proposing the first mathematical model for neural networks, laying the groundwork for future AI research. It was basically the main building block. They proposed a simplified model of neurons as binary units, introducing the idea that brain-like computation could be replicated with logic-based neural models. Basically, how to model your neuron, your brain, into a computer with binary bits. McCulloch and Pitt's pioneering work gave the word foundational blueprint a way to, conceptualize logical through thought process in terms of simple neuron-like units. This breakthrough established the basis element of human cognition, like reasoning, pattern recognition, and decision making, and that it could be represented and processed by mechanical means, by machines. Yet, at the time, as the theoretical groundwork solidified, a new question emerged. How can we determine whether a machine can genuinely think like a human? And that's what Alan Turing uh, tried to talk in his paper. And that's when he entered the scene. In 1950, Turing proposed the imitation game, now famously known as the Turing test, shifting this conversation from modeling the brain's architecture in the machine to interrogating a machine ability to produce human-like responsive and behavior. Basically, what the Turing test does is that you have one person, and he's talking through a chat to two different channels. One channel is a computer, a machine. One channel is a person. And if the person who is chatting with both the machine and the person cannot tell if the which is the person and which is the machine, then the test succeeds. So basically, the test is I don't know if the guy or the person says I don't know which one he's a human, then the test succeeds. And that was achieved around like 2015, I think, like almost 10 years ago. And so Turing, with this paper called "Computing Machinery and Intelligence," he like if you know Turing, he's really important, and not only in terms of AI, but in terms of computer science. He made a lot of contribution in terms of calculation, and also during the war to help resolve the Enigma, to crack the Enigma code, and also many mathematical theorems and stuff. And that's why today we have the Turing Prize, which is the equivalent of the Nobel Prize for computer science. And it was in its honor that it was created. Then skip to 1956. It's the first time that at Dartmouth Summer Research Workshop and Conference. It's a big university, Ivy League in US. That John McCarthy coined artificial intelligence word because it was not widely used at that time. There was no artificial intelligence mentioned, and the term was used the first time by McCarthy, and they predicted that human-level AI would be achievable relatively quickly and established AI as a field of study. So people started actually specializing in artificial intelligence, starting that point. In 1966, we have the very first rudimentary chatbot, ELIZA, by Joseph Weizenbaum. It was like very rudimentary, and it was one of the first chatbot, and it was simulating conversation by just doing pattern matching and substitution methodology, demonstrating the potential for machine to process language. That was one of the precursors to conversational agents that we have today, but it was very limited. And during the 60s, 70s, and 80s, we have what we call the ice age of AI, because there was not much investment. And even though they were contribution and some things, nothing really notable until 1986, when neural network resurgence, backpropagation was it existed, but Geoffrey Hinton, a major actor in AI, who will become later the godfather of AI, they published a pivotal paper on backpropagation, a method for training multi-layer neural network to learn complex patterns from data, which became really a cornerstone technique in the development of deep learning. And that's when we start talking about deep learning. That's confirmed. On another hand, it's in 1997, we have Deep Blue, which is a chess computer. And for the first time, Deep Blue won at chess against the world champion Garry Kasparov. And it was the first time a machine defeated a world champion in chess and other things. And it proved that computer, though there is a significant difference, because Deep Blue was not using AI. It was using pure search algorithm and brute force computation to to imagine all the possibilities and beat someone. It was not using artificial intelligence, but it proves that machine can beat humans. So even though it was not using methods in AI, it proved the point to the public. And the deep learning started really to break through starting in 2006, and that's when everything starting to fall apart for the better or for the worse. Uh, in 2006, we have the deep learning renaissance led by Geoffrey Hinton, who was named the godfather of AI. And they published a paper with Benjo and Yann Lequin, which is the current chief of AI at Meta. And that's what awarded them the Turing Award in 2019, by the way. And so what convolutional neural network did is that the improvement of algorithm hardware, GPUs, initialization technique allowed deep neural network to outperform previous methods in speech recognition, image classification, and it basically influenced natural language processing research, and it introduced the concept of deep belief networks, and really showed and demonstrate the efficiency of training of deep neural networks. We're going to explain a little bit. I'm not going to go too much into details, but Stefan is gonna explain a little bit more about how it works inside. Uh, don't worry if you don't understand everything I say. It's not really important. Just uh, just saying stuff. But basically, what CNN is, the convolutional neural network, is the foundation for everything that basically at the time Amazon was doing for product recommendation, or the basis of Apple doing facial recognition to unlock your phone. That's what the basis is for. Uh, and the next step is ImageNet. The next Rainer, can you cut your microphone, please? Okay. And after ImageNet is was created by Faithfully, and what ImageNet is, it's a massive collection of labeled image. So basically, I think there was like 14 million images divided in tags, basically like a cat, a golden retriever, a spider, and there were 20,000 categories and 40 million image. She didn't do anything with it. She just provided the data set, so the images with the labels. And the openness of this and the availability of this data set was for a researcher to do something with it and to use deep learning to do something about recognition, and that's what happened. Uh, the breakthrough moment of ImageNet came with AlexNet in 2012, uh, and that's what's called the Big Bang of AI. Basically, AlexNet was a deep learning model with remarkable accuracy at classifying this image. Basically, it was developed by Alex Krzyzewski, Ilya Sutskever, and Geoffrey Hinton. Geoffrey Hinton, the godfather of IA, and Ilya Sutskever is the co-founder of OpenAI, one of the co-founder of OpenAI. And basically, why is it called the Big Bang of AI? Because it achieved significantly better accuracy than previous approaches by using several innovative techniques. It used multiple layers of artificial neurons, hence that's why we call it deep learning, GPU acceleration, handle complex calculation and various other clever methods. And this network success in recognizing objects in images that was so dramatic that it helped sparked the deep learning revolution, convincing many, many researchers and companies to shift their focus to deep neural networks. This architecture, AlexNet, became the foundation for many modern AI vision systems we use today. Uh, we continue with pretty much the same people. So Ilyas Skever, which was the co-founder of OpenAI and was working at Google at the time, he created the recurrent neural network and sequence to sequence, which is basically the start of everything we have today. So how it works? It's basically you have an encoder and a decoder, and let's say the encoder is like the interpreter listening and understanding the first person, and the decoder is like the interpreter formulating and speaking the translation to the second person. So it's really good for interpretation. For example, common application use case for this was language translation, text summarization, answering question, speak recognition, code generation. This was the basics of everything. But this was not enough. Uh, the There was something missing is that sec to sec was doing things one word by one word or one token by one token, predicting the next one. What was the real breakthrough was done by Google in the paper called Attention is All You Need. And it was the invention of the transformer architecture. So basically what the transformer architecture is, and transformer architecture, I can't stress this enough, it's the mother of modern day LLMs. LLMs are transformers. Basic LLMs are transformers. Now we have much more complicated stuff, but they are transformer at the base. And that was the start of everything that we have today with all the GPTs, the cloud, everything. Um, what they did is that they focus on attention. So what is attention? Basically, what sequence to sequence was doing is that it was doing word by word deduction of the next word. Attention is looking at the whole sentence. For example, uh, uh, let's take a sentence. The dog was sick, so I took it to the vet. Uh, what sec to sec was going to do is it was going to check then dog was sick. It was checking word by word and doing some decoding. But what attention is doing is that it's taking the whole sentence, the whole input, and it process it in parallel. So it can link, for example, dog and it together. It can link vet and sick together. And all this connection happens simultaneously and parallel, which really, really, really improve the way that large language model and transformers are working. And Stefan is going to explain a bit more about how it's working, but that's really, really where all it started. And after that, well, this is basically the history. We had BERT with Google and DeepMind. Then we had the GPTs that we all know. For example, BERT was not a large language model. It was a language model. The difference between large language model and language model is just the number of parameters and the size of the data set. So, as I said, that's when all started with BERT and GPT. And GPT was released by OpenAI in 2018, and it was trained. No, it had 150 million parameters, which is nothing compared to what we have today. And in GPT-2, they have 1.5 billion parameters. And that's what's happening with those models. They keep doubling of tenfolding the number of parameters and the size of the data set. And GPT-3 was 175 billion parameters. And actually, GPT-2 was kept from the public because OpenAI was afraid that it was going to be too powerful, and that's why we didn't heard much before ChatGPT came out about GPT-2 and GPT-3. You could only access this through API, and you had to be selected in a list. And basically, that's what we have today with chat and generative AI. So chat is just an application of the LLM. It's just the usage of GPT. You take the prompt of the user and you give back the answer of the LLM, and that's not generative AI. And ChatGPT was released in the end of 2022, and that was the wow moment for AI. But that was the start also of leveraging AI for other things, like generative AI, which was, for example, 11 Labs was doing text-to-speech generation. Midjourney was doing text-to-image generation. And that's what we call generative AI. And I'm going to stop there because it's enough, because after that, there were so many applications in AI that now, as of today, there are more AI tooling that is going out than JavaScript framework. It's going crazy. So there's no point going further than this. But this is the history in AI. And now I'm gonna give the hand to Stefan for the continuation of the press.
Yeah, thank you, Gaëtan. So as you can see, there are a lot of different kind of AIs, different tools, especially nowadays. So to keep it simple, quote unquote simple, and to avoid looking at all the different kinds of AIs that we have today, I propose we focus on one of the most, if not the most publicly well-known category of AIs today, which are large language models. So large language models, one of the main part of it's the word model. The question is, what's a model? A model is a simplified description, especially a mathematical one, which is used to help predict, to help process calculations, and to have the next step in your reasoning. And of course, the other part is language. Just as a reminder, language is the structured system through which communication happens, which consists of grammar and vocabulary of words. So the question here is, come on.
You can't.
I can't? Yeah, okay. So LLMs are structures that allow language-based predictions. In other words, it's like a prediction machine for text. So the question is, how does it work? How do they work? I'll give you a hint. It's not a fortune teller in a box. The question you can ask yourself is, what kind of structure can predict language? But first, what kind of structure can predict at all? I can give you one example of a structure that can predict things. It's your brain. The brain can predict if I start a sentence, I know how I'm going to finish it, and probably you know too how I'm going to finish it. How does this happen? I'm not going to enter into details in neurology and science of the brain because first, I don't understand it. And second, all of the prediction happening in AI is simplification of this. And if you remember, the first part of the history that Gaëtan talked about was neural networks. And this is really the basis of AI, of today's AI. If you zoom into a brain, what you have is a network of neurons. And if you zoom a bit more, you can have something that can be modeled like this with multiple layers, a neuron layer at the start, a neuron layer at the end, and in between neurons, which are connected to one another. So all of this network can be assimilated to a brain. And it's what modern days AIs are using to model their prediction. So if we zoom again, we have one neuron. It's a very small part of the brain of the network. A neuron is composed of inputs, which it gets either from the outside world or from previous neurons from previous layers on the network. The inputs are weighted, so they are multiplied by some value. A function is used on all the values, and then the neuron is producing an output. Oftentimes, the function looks like a sigmoid, so some kind of flattened S. And for active or inactive considerations, the neurons are considered active above 0.5. Sigmoids, here it's a high pass filter in the example, they are used to clamp the output between 0 and 1. All of this happens simultaneously on all the neurons of the layer through a mathematical matrix multiplication. The process is repeated for each neuron in each neuron layer until the output is reached. And we can give an answer or estimate the answer based on the output neurons. I'll let you see a small example of how it looks like when it happens from an episode of Mindfield by the creator of Vsauce, Michael. Normally, it should be watchable. There's no sound. Okay, I'll comment it on the same time. So here, Michael is drawing an 8 on a list of pixels, little squares, and he gives the pixels to specific people that are on the input layer. So each of these people have specific instructions. They have to either get up or stay seated, whether they have some black on their pixel or not. Then people on the next layer will either get up or stay seated based on rules that they have. So they explain all of this orally. I will let you search for the video if you want to look at it yourself. But here they are showing which people did get a black pixel. These people are getting up. Behind them, the people that are looking at specific neurons on the layer behind them are getting up. So for instance, this guy here, he is a neuron that specifically detects straight lines on a horizontal plane. The 3 people that he's watching gets up, so he gets up. And the next layer is another kind of processing of the input. And all of these layers, they are doing increasingly complex checks in a way up to the end layer that has 1 neuron for each possible digit of the system that it can recognize. And one of them is supposed to be getting up because of all the rules that he applies to the people in front. And as you can see here, it works quite good. The neuron that represents the number 8 is getting up. No. Once is enough. So all of this is a simulation of a neural network. Each people represent one neuron, and each step of this process is the simulation of the processing of the weights, the calculation, the activation, and then going to the next layer. So a neural network in general and AI that relies on neural network works a bit like this. But of course, all of this is about numbers. We have either a 0 or 1 in input. Do I have a black pixel or a white pixel? And then at the end, we predict from 0 to 9 in digits. So we have to have 9 neurons on the output layer because we predict 9 different digits. I guess you can imagine that large language models do not have one neuron for each possible word in every language on their output network. So something different has to happen. And for this, no, next slide. Yeah, for this, as Gaëtan told during the history, the main breakthrough was the how to predict language. The main breakthrough was the transformer architecture. So it's the real architecture that LLMs today are using. And for this, I have another video to propose to you. I put the QR code that you can scan if you want to get the link to the video. This video is around 40 to 45 minutes, something like that, and it's explaining the whole thing much better than we can do here in a short time. But in order for you to have the image in your mind of what a transformer architecture looks like and how we can go from numbers or from an input that is text to something that calculates numbers to text in output, I propose that you have a look at this. So maybe I can skip a bit. No, I can't. Okay, so he's talking.
When do you want me to
No,
put the?
it should be okay because it should not go above 40 seconds or something like that. So maybe before 40.
Yeah. All right, wait.
Yeah, or around 20 must be okay. This is too far. Yeah, this is okay. So the transformer part, the idea is that transformers are multiple multi-layer neural network that do their calculations on big vectors, and these vectors are the heart of pause it here. Yeah, the the vectors here are the heart of the LLMs. Vectors are big lists of a lot of numbers, and these numbers, these vectors, are assigned not directly to words, but to tokens. And tokens have a fixed size, like 4 characters, for instance. And every possible token, so every possible combination of 4 characters, is transformed to a big vector, for example, 1,000 numbers. These vectors are then processed through multiple neural networks. And the output, which is also a vector, is then converted back into tokens. So this is how LLMs go from a text input into tokenization, into calculations on numbers, and then a text output. So I really, oh, it's only 27 minutes, the full video. So I really encourage you to go have a look at this video, because it's very complete and it's explaining the whole thing, very visual and very efficient. So the next question we can ask is, how are they made? How are they created? So it's mainly a 4-step process. The first step, of course, is data collection. So you have to find data and you have to prepare what we call the data set. It can come from diverse sources. It can be books, it can be articles, it can be web content, web pages. And the data that you collect needs to be prepared for training, and it needs to be cleaned up. For instance, you can convert it all to lowercase, you can remove stop words, you can tokenize the words into token sequences and so on. But you have to do a big work upfront to collect and prepare the data. Then you have to decide on your model configuration, which is to say you have to decide the architecture. So the different kind of parameters for your transformer, the hyper parameters, how many layers you want. And these parameters, the hyper parameters, are things that you can then later tweak to have a bit more of control on what and how your LLM works. Usually, the researchers experiment with different parameters here to check the output and check how it is and if it's good enough or not. Then, of course, you have the model training. So model training is giving the data to your neural network, to your transformer, and then checking the output and doing it again and again to tweak all the weights that are inside your transformer. One thing I realized I forgot to clarify, Gaetan spoke of, for instance, GPT-2, GPT-3 with billions of parameters. These billions parameters are the numbers that are in the vectors that the neural network is processing. So when we say GPT-3, for instance, have 175 billion parameters, it means it has 175 billion weights for all the neurons in the network. So this model training is a cycle that runs the model, checks the predictions, modifies the weights, and then repeats millions or even billions of times, depending on the size of the dataset, until the model achieves the optimal performance or the perceived optimal performance. Of course, you can imagine that the computational power for this is huge. And to reduce training time, usually they are parallelizing the calculations, distributing the calculations through a lot of GPUs and so on. And the last part is the fine-tuning of the model. So it's when you have your trained model, you have 95% of the tweaking done. And then you can tweak the hyper parameters and modify a bit the structure of the model to make sure that it's doing the specific things you want to do precisely and correctly. So of course there are challenges with this process. The first of them is the data collection. So if you have to collect data, you have to do it well. The main challenge is to find good data that data that is pertinent for your case and for what you want to do, and in sufficient volume. If you are OpenAI and you want to create a chatbot that can discuss with people of all the languages in the world, you have to find texts in all the languages in the world to give your model. And these texts have to be correct in the language. They have to be well made. They have to make sense and so on. So this, of course, can be a challenge. I guess not everybody in OpenAI speaks every language in the world. So verifying the output can be also some kind of a nightmare. Then, of course, you have the computational power problem. The computations are very resource intensive and can cost up to millions of dollars. The training time, which is directly tied to the computational power, the more power you have, the less time it takes, but it can take months to train a large language models today. And in the same category, we have the environmental impact of all of this, because if we have thousands of machines that are running 24/7 to do a lot of calculations, the impact can be very, very huge. Some models can have a carbon footprint equivalent to several cars over the lifetime. So there is an echo.
François, merci.
Test. Okay. Of course, these are the main challenges. There are a few smaller ones. And the last step in the process was fine-tuning. So we wanted to focus a bit on what is fine-tuning. Why? Well, first, because as you can see, creating a large language model from scratch is, I won't say very hard, I would say it's impossible for all of us, unless we have millions or billions of dollars and a lot of time and a lot of skills. It's too late, and it's not advisable to try and create new large language models. Today, what people are doing in our category of work is more like fine-tuning the models. So what's fine-tuning? Fine-tuning is adjusting a pre-trained model, an existing model, to make it do better something that you want it to do better. So already large language models are very good at doing a lot of things, and later Gaetan will talk about that. But they are general to they are trying to do everything correctly. Fine-tuning is the process of making a model do specific things better, even if it costs other imprecision or doing something that you don't care about to be less good. So it's done by adjusting the weights of the model. So playing on the emphasis on some things and some others. The challenges and the limitation of that are a bit similar to creating a large language model, but they have much less big scale. So it's a bit the same with the data. You have to collect data of sufficient size and quality, but this data does not need to be general because the general part is already handled by the LLM. The data has to be specific to your problem. So let's say, for instance, you want to create or to fine-tune a model for, I don't know, creating a live chat to help people navigate a website on a government site, for instance, you take a pre-trained model and then you give it data that is specific to that government site, to the things that people will do there. You can give it, for instance, sample questions that people are known to ask on these kind of sites, things like that. And here the quality of your data is very important because it's what will guide the end result of your fine-tuned model. One challenge that exists specifically for fine-tuning is the extra cost associated with having to train and especially having to host your own model. Of course, if you use, I don't know, like OpenAI's GPT or things like that, you can ask the globally available AI through their API. If you want a fine-tuned model, you have to host it yourself and give it your own API to query it. A bit like the LLM creation, you need to repeat the fine-tuning. You have to do the trial and error process of fine-tuning your model, checking the output, evaluating if it's what you want or if it's not there yet, and do it again and again in a cycle. So fine-tuning is almost a never-ending process of making the model better. And of course, if the base of your fine-tuning, like the model, is updated and you want to benefit from the updated model, for instance, you fine-tune GPT-3 and now GPT-4 is out, and you want to benefit from GPT-4 base, you have to repeat the process with GPT-4 and refine-tune from GPT-4. So the process looks a bit like that. You take the pre-trained model, you give it training data, like gigabytes or terabytes of data, which is composed of a prompt and an expected completion. And the model will use these to adjust the weights to become more biased towards giving you the completion you expect for the prompt you gave it. This data is what we called labeled data, a bit like what Gaetan talked about with the ImageNet of labeled images. It's called labeled because you tell the model what's quote unquote the correct answer is for the input. Unlabeled data, on the other hand, is what you would have when you and I talk with ChatGPT online. You give it an input, he gives you an output, but there was no expected output from it. So the data you gave it, the input was unlabeled. So with or without fine-tuning, the LLMs are capable of doing many different things. One question is important to consider is what can LLMs do great? And for that, I will give back the voice to Gaetan.
Thank you, Stefan. So yeah, no, do not put your mouse there. Down.
I will stop the control.
You lost the control?
No, I will stop it. I guess I don't need it anymore.
Okay. Okay. Yeah, it's important to wonder to know actually what do they do great and what they don't do great and what are the limitations. And for that, I will explain. Try to be a bit quick because it's already almost time. So they are great. First of all, are language understanding and generation. They can do great coherent text generation, producing human-like prose stories, blog posts, articles with somewhat very fluid narrative structure. They can draft emails, reports, written responses that are contextually appropriate and stylistically consistent. They have a contextual understanding. They interpret the user queries and prompt with a high degree of nuance. They understand implied context, reference, and some conversational subtext. They are creative at writing and brainstorming. They are great assistant in idea generation, for example, for fiction, for marketing content, for scenario planning, for many brainstorm. It's a really usually when you brainstorm with people, you're gonna have a limited number of answer, but with LLMs, it's unlimited, and they offer also alternative phrasing, metaphors, plot points, and enhance creativity. They are great at information retrieval and summarization. They can summarize complex information, condensing lengthy documents, articles, research papers into concise summaries. They can extract key points, highlights, and actionable insights from extensive text corpora. They're great at Q&A, providing answers to factual queries based on learned knowledge. They can explain concepts, historical events, technical details, and general trivia. They're really awesome, as we said, about translation, cross-language understanding, translating text between numerous language with improved fluency and accuracy. They can understand cultural idioms and context in different linguistic settings. Uh, and they're great language learning assistants. They can be really great tutor in helping you learn a language because they can explain grammar rules, provide vocabulary, simulate conversational practice, etc. Uh, this is I guess the most use we have as engineers is that they're great at coding assistance and technical support. Coding help, they can generate code, completion, snippets, debug strategies, explanation of algorithms, generation of algorithms, uh, performance improvement, optimization. They can provide for you the documentation and the comments for existing code base. They're also great at technical documentation and explanation, breaking down more complex technical topics into simpler explanation, crafting guides, manuals, or step-by-step instruction for software usage. They're great also for rapid prototyping of ideas and drafts, for example, outlining and structuring context, offering outline for essays, presentations, report, business plans, any kind of documents. They're great for brainstorming content flow, argument structure, thematic organization, for proofreading and editing, um, suggesting improvements to clarity, style, and grammar, rewriting or refining paragraphs to maintain tone and consistency. They can be really good at domain-specific knowledge application if you giving the training data. For example, they can simulate or emulate an expert, as I said, within the training limits. So within the data you fed it. You can discuss topics in law, medicine, finance, science, and varying degrees of sophistication from beginners to experts. It can act as a study aid, providing explanation and insights relevant to a given field. For example, personally, when I read a book, I like to have my AI assistant, my personal AI assistant, next to me to, for example, if I have a point to explain to me more in details, I can just ask whatever the book, it will know the answer. Except if it's really no new book, but we'll see about that later. They're great at conversational agents, serving as chatbot or digital assistant in customer support, educational platforms, for interactive tutorials. They guide users through troubles, shooting steps, FAQs, best practices. Now that was the good side. What is the downsides and the limitations of LLMs? First of all, it's their reliability and accuracy issues. And the main problems are hallucinations, which are fabricated information. LLMs may produce confident but incorrect fact. And it will be really confident about the incorrect facts, which is problematic. And even if you're wrong and you say that confidently to the LLM that something that is wrong, it may agree with you and hallucinate with you, which is really something you have to work on when working with LLM. It can misquote sources, like mixing source from somebody said something, but it was not exactly the real person who said it. Invent details due to their pattern-based training. They detect patterns. So if they have similar patterns, they can like mix some kind of information. They lack a built-in mechanism to verify or fact-check the outputs, like a reasoning mechanism. Like, for example, there's some things that we start to see right now is that they do an output and then they can fact check the output that they did and correct themselves. That basic LLMs cannot do that. But now we are starting to see some who are doing it. They have incomplete domain expertise, although as Stefan said about fine tuning, they're really generalist. Basically, they can discuss special fields. They might not understand all the time nuanced concept or fail to recognize their own knowledge gaps. They think they know everything, but they don't. They cannot guarantee correctness, especially for tasks requiring domain authoritative accuracy. And I cannot stress that enough because I've seen many cases in medical and legal advice where doctors and attorneys were using ChatGPT for their arguments or to diagnose patients, and it failed miserably. Uh, you can check on that. It's laughable. Uh, Second problem is the bias and ethical concept. Inherently, LLMs are ingesting billions and billions and billions and trillions of data. And this large uncurated internet data can introduce societal, cultural, gender, racial biases, and many more. They can inadvertently perpetuate stereotypes or offensive content and illegal content and criminal content. They can output offensive or harmful prompts. Without careful filtering, LMs may produce desired content, hate speech, harmful language, and some really ethical oversight and moderation layers remain crucial for LLM to be allowed to exist. So the third problem is the lack of true understanding. They have a shallow pattern recognition. LLMs generate text predicting likely sequence of words, not by reasoning with true comprehension. They're guessing. They are not reasoning yet. Even though we are seeing reasoning now because it's just building and cycling on the output, it doesn't really reason. It's guessing more accurately step by step. They do not possess genuine understanding, emotions, or consciousness. They do not have reason. They cannot reason about external context. LLM struggle with tasks requiring logical deduction, mathematical proof, deep reasoning, not explicit demonstrating in training data. They have troubles with integrating external real-time information not present in their pre-trained knowledge. They're sensitive to input prompts. Minor variation in your prompt wording can cause significant different responses, making behavior unpredictable. requires careful prompt engineering to yield consistent desirable output. So you have to be always, if you want the same result, always put the same prompt. And even so, it's not going to be exactly the same, but at least it will be as some level consistent. They have a limited long-term context management, and this is a big problem because although some LLM have extended context window, there's still limits that they have still limits that they make following very long dialogues or documents very challenging. For example, big code bases and exchange. A lot of us have experienced this. Forgetfulness of a long context can lead to contradictory or repetitive outputs. For example, you start a chat with an LLM, with ChatGPT, Claude, or anything, and the longer the chat becomes, the bigger the context window will be, and the less accurate it will become. They are challenged with temporal and cultural limitation. They have stale knowledge because the LLMs are fixed to the time they were trained on. So they were trained on static dataset, and they do not automatically update their knowledge. They may provide outdated information or fail to recognize recent events. They have struggled with interpreting subtle cultural references or evolving social norms. They may also misinterpret humor, sarcasm, or context-specific nuances. And last but not least, problem is the dependence on large computing resources. Large models require substantial computational power for training and inference. This can be expensive for the environment, costly, and limiting accessibility. You also have problems with latencies. Serving large models at scale can lead to latency issues, making them less practical for real-time applications. Techniques like, for example, model compression and distillation help, but not always without performance trade-offs. So now let's talk about the future and make a somewhat happy conclusion about this. In the short, medium, and long term, like let's say, so the sentence at the end are just some jokes I made. You can read them, but it's better to listen to me. So for now, right now, we're expecting, and we are currently living in the implementation of technical and ethical safeguards. That's the most important thing we have to work on. They are enhancing fact-checking and reasoning tools and prompt engineering techniques, making responses more reliable and context-aware. And we are currently already seeing seamless integration of LLMs across various sectors like educational, marketing, customer support. And this is today. In the medium term, we're somewhat already seeing and will continue to see specialized LLM in domain-specific expert. We're going to have LLM specialized in law. We're going to have LLM specialized in medicine, in engineering. We already have LLM specialized in code, but not exactly in law, medicine. But it's starting, and there will be more and more experts LLM because it's going to ensure more credible and authoritative guidance. The emergence of multimodals capable of interpreting text, image, audio, video, everything at the same time, using the most senses they can to offer a more holistic understanding of context. And improve the capacity to maintain, extend context over long conversation and document. This is about the context window. This is what we're going to see, is that they're going to be able to ingest more and more information and keep the knowledge without losing the accuracy. And in the long term, we're going to see models capable of continuously updating themselves. So not only with static dataset, they're going to incorporate the latest news in real time. and they're going to be able to justify their response and verify the reference in the output to correct them. They're going to be able to fact check themselves. They're going to be able to have somewhat of a even more better reasoning, even though it's not going to be real reasoning. It's just going to be more and more power. AI will play a greater role in collaborative decision making for scientific research, public policy, and product innovation. And we are going to see, obviously, a co-evolution of human and AI capabilities, with humans contributing creativity, ethics, and intuition, and AI providing breadth, precision, and analytical speed. Yet, there's a real dilemma and problematic about ethics and responsibility. There is an absolute necessity of aligning AI with human values, such this is not limited to, but fairness, transparency, privacy protection. Uh, AI and big conglomerates and open source and companies, they have to collaborate with researchers, governments, businesses, NGOs to establish standards for the world, for Europe, for US. Everybody, we need standards. We cannot have private rules about AI. Regulation is a must. Um, we need vigilance, public engagement, and education to prevent AI to become an uncontrollable black box to people. It has to be clear to people that there needs to be an education about AI, because AI is going to be with us and it's here to stay. It's it's not going to go anywhere. It's just going to grow bigger. The final message that we wanted to pass is LLMs and AI are powerful tools that, when guided by human wisdom and responsibility, can unlock unprecedented creativity, innovation, and problem solving capabilities. I invite personally everyone to participate in this journey by asking questions, reviewing AI outputs, ensuring inclusivity and accountability in AI deployments. You can do it at your scale by correcting ChatGPT, by correcting all those LMs. AI is here not to replace us, right? AI is not going to replace people. AI is not going to replace developers. AI is not going to replace some. We will adapt, but it's here to augment our abilities, inspire new ideas, and help us imagine a richer, more collaborative, and more enlightened future. That's my conclusion to this, our conclusion to this. Maybe it's too much of a dream with butterflies, but that's how I hope it's going to be. So if somebody or anybody have questions, we Stefan and I are here to answer. This is the end of the presentation. Thank you very much. You can raise your hand or okay, Senor, let's go.
No, I wanted to clap. I don't know.
What?
I wanted to clap, not to raise my hand.
Okay. Well, you can. Okay, I will do the clapping for you.
Thank you.
If you're not comfortable asking questions in English, you can answer in French, and we will translate. No problem. Juste posez votre question en français, on s'occupera du reste. Not even in French, okay? Maybe in Spanish.
I have a question.
Yeah, okay.
You said that AI should not become a black box. Isn't that the case already? Like I heard that even people who built it, they know how they do it, but they can't debug or like they don't really know how everything works inside.
Okay.
Is it right or is it illusion?
So, and there are many levels to this. I did not say it cannot become a black box. I said it can become an uncontrolled black box,
Ah,
uh,
yes.
which is different. And to answer your question, uh, it certainly is a black box, but there are tools. For example, the community had one company came to us and made a talk to us about like they are able to backtrack the LLM to ask and know what weight, what criteria made the LLM take this decision, make this output, like Stefan, the company you introduced, and that came for us. So they built their business model, and they're really, really, really smart people. And what they're doing is that they when the LLM is open source, it's easy because the weight are everything is available, so they can trace, so they can ask a question and you have your answer, and they can know which weights, which criteria were taken into account the most for the output. For example, the question the person who was talking, she asked. The set of data was the salary of people in the United States, for example, and the question was, uh, I'm a well, I'm a woman with Asian. No, I'm a woman named Charlie, and I live in New Jersey, and I want to know what would be my salary if I was doing if I was being an attorney. And then the response was like, for example, 150,000 a year, and it said it was like you had like some how do you say camembert, like some like you
Pie
have
chart.
statistics. Yeah, pie chart.
Graphs.
Thank you. You have pie chart like about like what was taken into account to give this salary. And for example, there was obviously the race, the gender, and some other factor like the fact that she had a high education, like all those things. So you can see what are inside the LLM. It's not totally a black box. There are tools that exist right now, even with non open source models, that you can know what's happening inside. What I meant by becoming a non-controllable black box is that people needs to be educated on how to use AI and not just blindly trust an AI or LLM. That's what I meant. But there are tools that exist to know what's really happening and what gave you this answer. Why?
Okay.
Obviously, it's very expensive and you cannot afford it, but we cannot afford
Ah,
it.
you don't know. Maybe I can.
Oh, okay. Yeah.
Thank you.
One thing I want to add to your answer, Gaten, is that this is part of what makes artificial intelligence useful to us. If you go back to the history that Gaten presented, Deep Blue was a collection of how do you say, conditional branches. It was like a big list of ifs and elses that were designed to guide the process decision based on the board status and things like that. But every part of the algorithm and every part of the cognitive behavior was explicitly coded into the tool. With what we have today with LLMs and what I've presented on the transformer architecture and the mathematical calculations, it's a structure that allows new things to come out of what has been created. There is no place inside LLM where you have a check if input contains woman, divide salary by 10 or something like that. It's simply a result of all the weights that have been given to the tokens and things like that to predict some kind of output. And because we don't have every possible combination of inputs available, we can't know and predict every combination of output. That's what the AI is here for. So it can't not be a black box to be efficient.
Yeah, basically, it has to be somehow a black box in terms of you don't really know what's gonna give you the answer, what exactly the answer is gonna be, because it's not deterministic. It's not just rules. There's no 100% sure what's going to be the result. So it is somewhat a black box, but you can know afterwards what happened. But the beauty of the AI is that it is going to be reasoning, not reasoning, but it's going to be thinking on it by itself and give you the answer that you cannot predict.
Yes, Raphael?
Yes, Raphael?
Hello, guys. A small question. AI has a very bad press in terms of environmental impact. And I would like to know what you think about that and what way could we have to integrate it into the responsible digital technology?
Yeah,
Yeah,
I will.
you can go first. Yeah.
Yeah, I will let you answer. I don't think we have the same part of the answer. In my opinion, we are living in a time where we have something that is akin to industrial revolution. In the ancient times, the farmers were working the land with their arms and with static tools like forks and rakes and things like that. And then someone came around and invented the motors, and then came the tractors and the agricultural machines. And all of these, the cars, the machines, the motors, and petroleum in general has had, I think, the worst kind of impact on the environment yet. And I think with AI, we are adding on top of that mountain of environmental unfriendly things. So yes, the impact is huge, and sadly, we could not do without the motors, without the cars when they were invented. I think we are not going to be able to do without the AI now. And if history serves, we probably should act as soon as we can. When I say we, I mean the human race in general should try and be more responsible and look further into the future than what people in the Industrial Revolution did, to try and create something that is not going to destroy the planet in 20 years. And sadly, I don't think we are doing that, but I don't have any real view on what's been done or not to this extent.
Yeah, I can complete your answer, and I have another thing to say about this. So first of all, we are not doing anything for the agreement of COP, the Paris Agreement that said that we needed to reduce by 10% the CO2 emission by I don't know 2030 or something like this. This is not going to work because not because of AI, but also because of many other things. And now that we have the biggest actor in terms of industrialization, and the next Trump president going to be disastrous for the environment. And for example, just like a few days ago, he said that he will he will give a free card in terms of environment to any company in the world that invests $1 billion in the US. So basically, if you have 1 billion, you can go to the US and do anything about the environment that you want. It's not only about AI, it's back crap crazy what he's doing. But let's go back to AI. For AI right now, I think it's stabilizing right now, because even though we still need a lot of compute, we have achieved some kind of a plateau in terms of LLM and resource. So it's stabilization. There is a stabilization in terms of compute that we need. And what we're seeing, especially in French government right now, I did an hackathon for French government mobility, and the key takeaway was to use frugality in LLM. And frugality in LLM is basically using large language model that can be used in portable devices that are really small. And when GPT-2 and GPT-3 was doing, now you can have this power on your smartphone. You can have this power on your computer. You do not have to use the big LLMs trained on 175 billion parameters to be able to do a really good chatbot right now. Every example I saw during my experience and the teams that were doing this, all the LLMs was running on their machines. So us, for Key Consulting, for example, we are not going to propose to the client to use an external LLM provider like OpenAI, Anthropic, Gemini, or anything. We're going to propose them to host their own LLM. And this is way less greedy in terms of money. And open source models like Quen and Llama are doing a great job right now. Even with 7 or 3 billion parameters that you can host, it's just 3 gig and a bit of CPU and RAM, still significant, but a lot less significant than what a million GPUs NVIDIA is using for powering OpenAI. So to answer your question, there is a real effort in frugality right now to use LLM that can work on your machine and have pretty much the same result as big LLMs. And that's what clients want already. So the effort is to turn ourselves on using open source and tools like Olama or Stability or Llama Index and Langchain and stuff like this to make it work on your computer and on your smartphone. And local LLM are, for me, the future, not big AI providers. I don't know if that answers your questions, but
thank you for the feedback.
Yes, Arno?
Yes, it was just to complete your answer. Well, I think, in fact, the impact on the environment is more in the side of training big LLMs and not in the side of using it. Because before you can use an LLM like Olama or anything like that, you have to train it. And that's the big part of the power consumed. It's not the, in fact, when you train your LLM, you create a trained brain. In fact, when you have the brain, you can use it for a chatbot or anything like that. But before, you have to train it, and that is what is very huge in power consumption. And there is also other problems that are existing about training LLMs. It's that about the data. I don't hear any word about that, but it grabs all data over internet without respecting all the rights, copyrights, or intellectual rights. I don't know how to say in English, but
Property.
property, yes. There is like something which is very weird in that aspect, because it doesn't respect human rights, in fact. And another point I wanted to say is that the use of IA in industry will probably destroy many employments. For example, the translator are very impacted by the arrival of AI, because lots of employers use now artificial intelligence instead of calling a person that did this job before. You see, there is more. There is a lot of things that we could be said about that. Right.
Okay, so to answer your, it's healthy criticism about AI, and that's sadly not something we can do much about. And if your argument about, for example, translator is companies should still hire translator to translate, it's not going to work, because companies are all about making money, and they will use the tools they have at their disposal, and sadly some job will I have a great example. Some jobs will disappear because of AI, but some jobs will be created. For example, and that was something that was shocking to me. You remember before the Industrial Revolution and before the cars existed, uh, every people were conducted and drove by horses. So there was a huge industry surrounding the horse breeding and for this. And then the car appeared, and this whole category of maintaining the horse and the roads and everything surrounding the switch from horses to cars start. Then all those jobs disappeared. And something changed. So this is not something unprecedented. This is just the way it is, and we have to cope with that. We have to adapt. So some people will have to find another way. It's sad. I'm not saying I'm not happy about this, but I'm saying we cannot do anything about this. It's how the world evolve and how technology solve problems and bring new ones and solve the other ones, so we don't need as much as we needed before. It's just the way it is.
Well, I think that's a point of view. It's fundamentally politics, but we cannot just go deeply in that question, because it's a big question. But there is lots of example that in fact there is something to do, but it's politics. It's a political point of view.
Yeah, I mean, if we are afraid of a future where the work that we do today is done all by AIs and robots, and the humans have to just lay back and enjoy, something is wrong with the way we are looking at work in general. I mean, why wouldn't we want to just be able to exist and have the things that we don't want to do be done by robots and AIs? I think we can conclude the presentation here. If you have additional questions, I think you can ask Gaëtan or I in
Yes.
private or in any channels that we have available.
Yeah. Just
I
to
don't.
answer, so
Yeah.
just one thing about the training. I know the training thing is not the case anymore. We will talk about this in the community, but training is not a problem anymore in terms of our resources. It's really what's important right now. It's running LLM locally, not using the AI. The training doesn't matter so much anymore in today's AI. It's not that much of an impact on the environment. Not anymore, at least. It was last year, but it's not anymore.
Things are moving fast. So someone asked for us to share the slides. I think we will try to have a shareable version. Maybe we will cure out the animations and the videos that are weird in a PDF or a slide. Also, I think you said it at the start, Gaetan, but this whole video will be available. It's been recorded and it will be available probably on YouTube with French subtitles.
Yes, I'll try to make the subtitles. We'll see.
Yeah, and I think that's it. So thank you all for coming and attending, especially at this time.
Thank you
and
very
sorry
much.
sorry for preventing you from eating. Thank you very much, everyone. Now I'm going back to my holidays.
Yeah.
Bye.
Bye.
Bye.